All right, well, thanks for joining me today. I am Eric Bjornstead, and I am the Technical Information Director for Bell Performance in Longwood, Florida. And today we're going to have a training session on the topic of cold flow handling or cold weather handling issues with diesel fuel. Now, in the time that we have together today, we want to aim to cover all of the major considerations that come out of this issue of diesel fuel and cold flow in the winter. By the time we finish, you should be a lot more familiar with how and why diesel fuels have problems in the cold and what to do with or what to do about those problems. So, specifically, the kinds of things that we're going to talk about today is we're going to talk a little bit about the chemistry of diesel fuel and the chemistry of cold flow, not cold flow constituents per se, but uh, components of the diesel fuel that play into or have causal relationships with the problem of cold flow and cold weather performance. We'll talk about how and why diesel fuel gels in cold weather. We're going to talk about the issue of ultra low sulfur diesel, um, how and why it was created, and how the changes to the diesel fuels to make ultra low sulfur diesel have impacted how those diesel fuels respond in cold weather. And then we'll also talk about fuel in cold weather situations, and we're going to what goes into an effective cold weather treatment for that fuel. So let's kick this off with a little bit of background discussion here. Now, what is the basis for what we're talking about here? What's the background? What happens to diesel fuels in cold weather? Well, petrodiesel, that's diesel fuel refined from crude oil petroleum. Petrodiesel contains large carbon molecules called paraffins or paraffin waxes. And these waxes, these paraffins, are already dissolved in the fuel as a part of its composition and makeup. As the fuel gets colder, as the temperature drops, these paraffins that were previously soluble in the fuel, they become insoluble and they precipitate out, appearing as seed crystals in the fuel. And over time, these crystals aggregate, they bump into each other, they increase in size, they get bigger, and when they do that, they then get large enough to be able to plug fuel filters and settle out in fuel lines, fuel distribution lines, and this because they end up gelling the fuel, they end up plugging the fuel filter and shutting off fuel supply to the engine, which then shuts off equipment operation. So one of the basic solutions to this, and we'll talk more about this in more detail later, cold flow improvers or CFIs. CFIs can be used to mitigate the negative effects of these paraffin crystals. And effectively, what they do is they lower the effective operational temperature that fuel can be used at in the winter. Uh, as we go on, you're going to hear some different terms. We've got three terms here that are defined, and we want to be able to define these terms so that you'll be more familiar with what we mean when we use them. Right now, we have three temperatures that are used to describe any diesel fuel, so the properties of the diesel fuel. And you're going to want to be familiar with these. The first temperature is cloud point temperature, and that is, as you can see on your screen, that is the temperature at which the fuel becomes cloudy when the wax first precipitates out. Um, so as the fuel cools down, this is going to be the first temperature that's going to be relevant because as the fuel cools, it's going to when it reaches this point, when it reaches this temperature, it's going to start to appear cloudy. So that's the cloud point temperature, and the fuel is becoming cloudy because little wax seed crystals are starting to appear in the fuel. And for most diesel fuels, for most number two diesel fuels, cloud point can be anywhere from 20 degrees Fahrenheit to -10. Typically, this -10 is probably more rare. So usually the cloud point, when we're talking about it with someone, we'll say 15 to 20 degrees Fahrenheit is reasonable for most number two diesel fuels. The second temperature is cold filter plug point. That is the temperature at which wax may be expected to plug fuel filters and thus interrupt the engine operation and cause problems. Usually, the cold filter plug point is about 10 degrees below the cloud point. That is why it's useful to know what the cloud point temperature of a particular fuel is, because if you know the cloud point, you can then, ballpark predict what the cold filter plug point temperature is. And the cold filter plug point, or we can refer to as CFPP, the CFPP temperature, that is probably the one that's most often referenced because it's the one that most directly speaks to the problem of trying to predict at what point you're going to have problems that you need to do something about. The third temperature is pour point. Pour point is the lowest temperature, so it's the last one that comes into play, and it is, as you can see, it is the temperature at which fuel gels enough so that you can't pour it anymore. Or another way to put it, it's the temperature at which any liquid, in this case diesel fuel, becomes semi-solid and loses its flow characteristics. So cloud point, cold filter plug point, and pour point. Now, diesel fuel naturally is a mix of different kinds of molecules, and these molecules range in different sizes, typically from, we'll say, C8 up into C20, maybe C18, something like that. Diesel fuel is heavier than gasoline, so it's going to contain larger molecules than gasoline will. And number 2 diesel is heavier than number 1 diesel, which is kerosene. So number 2 diesel is going to contain larger molecules than kerosene will. Now here you can see all different classes of molecules that diesel fuel typically will contain. You've got the paraffins here, which are these long chains of carbons. You've got naphthenes and aromatics, and aromatic is typically delineated by this thing here, this benzene ring here. You've got butylbenzenes. You can see all these ones: isodecanes, normal decanes, heptenes, olefins. These olefins are the ones that cause the problem with diesel fuel stability because you can get a lot of these kind of molecules formed when the fuel is undergoing catalytic cracking in order to take large molecules and break them up into smaller molecules that can be used to increase the yield of diesel fuel. You get more of these kind of molecules with these double bonds here, which are inherently more reactive and less stable over time than something like this, which only has single bonds. So the important thing to note here is that because diesel fuel is refined from crude oil, you've got there's 2 important things related to that fact. First is that no 2 diesel fuel samples are going to be exactly alike. There's so many different kinds of molecules that are present in the fuel. And you could have, I don't know, 30 or 40 different kinds of molecules, and then you have them present in different amounts. So no 2 diesel fuels, even though they're both labeled, on-road diesel or number 2 diesel, even though they're labeled the same, they're not exactly the same because they have different molecular makeups. The second thing is that because diesel fuel is refined from crude oil, it inherits some of the constituents that came naturally with the crude oil. Crude oil is a natural substance, made out of millions and millions of years of dead plant and animal life. And it contains a lot of different things, including some things like some metal content and some sulfur content. Now, they're able to refine out the metals from diesel fuel, but the sulfur tends to make its way into fuels like diesel. So diesel fuel has a certain sulfur content that it has inherited from its crude oil parent. And that sulfur content has been linked over time with environmental problems like acid rain. Excuse me. Sulfur, when you combust diesel fuel, the only thing that burns in the diesel fuel are the carbons and the hydrogens and the oxygen from the air. And when you burn a hydrocarbon, which is what diesel fuel is, if you burn it completely with the right amount of oxygen, then you're going to get carbon dioxide and you're going to get water. if the diesel fuel has some molecules that have sulfur, well, that sulfur is not going to turn into anything else. It's going to have to go somewhere. It goes into the process and it comes out of the process. And so historically what's happened is that that sulfur has oxidized in the combustion chamber and formed a gas like sulfur dioxide and sulfur trioxide. And those two gases would leave the exhaust and then they would go out into the air. And as they got into the environment, some of those sulfur gases would condense or combine with water vapor, and you would get acid rain, which, as we all know, is really, really bad for forests and plants. So the sulfur content of diesel fuel has historically been linked with these kind of environmental problems, and thus that allows us to segue into an important thing to remember about diesel fuel, and that is how environmental regulations have caused the fuel to have to be processed in different ways to change their characteristics. The Clean Air Act, which has been an act which has been in force for a number of decades, but it has had different amendments and different additions to it over time. Well, one of the additions, I believe, I want to say that it was in 1986, started calling for a reduction in sulfur levels or sulfur content for on-road diesel fuel. And so in 1992, all on-road diesel fuel required a drop in sulfur content from 5,000 parts per million, that's ppm, to 500 ppm, that's a 90% drop. So 90% is good, a lot less sulfur going into the air. Then that works so well that 2006, 14 years later, they decided to go at least another step further by doing a further reduction in sulfur content from 500 down to 15 parts per million. And that is where you get this fuel that is the fuel we use today called ultra-low sulfur diesel, or you'll see it abbreviated as ULSD. Now, it used to be that this only applied for on-road fuel, but now, this is 2016, so as we're halfway through the second decade of the 21st century, now that they have pretty much been able to make ultra-low sulfur diesel the law of the land for all kinds. It includes diesel fuel used in stationary applications like generators. So you have all this ultra-low sulfur diesel, and how do they get that? How do they take diesel fuel that used to be high in sulfur and turn it into diesel ultra-low sulfur diesel that has virtually no sulfur? Well, there are a number of different ways. It all has to be done at the refinery. That's the first thing we have to remember. So these are all refinery considerations, and they have a number of different options that they can employ in order to accomplish this. The primary one, the big one, is this one, hydro treating. They run it through some systems at the refinery, and they're able to essentially, I want to say scrub the diesel out. Excuse me, not scrub the diesel, scrub the sulfur out. And so they get a sulfur, a diesel fuel content that's a lot lower in sulfur, and that sulfur that they take out, it comes out as hydrogen sulfide gas, which they can capture, and then they can use it for other things like, industrial creation of sulfuric acid, stuff like that. So they can do hydro treating at the refinery. They can also do what they call distillation cut management, which is basically where when they're formulating the diesel fuel, they'll take out certain components of it that have higher inherent sulfur content, and they'll substitute other ones, and they'll mix and match in order to get a sulfur a diesel fuel blend that has the low enough sulfur content that they can send it out into the marketplace. They can also choose different kinds of feedstocks and different kinds of crude oils. There are certain kinds of crude oils that are naturally lower in sulfur. Now, there still has to be other things that's done to them. There's no crude oil that has 15 parts per million or less sulfur in it. But refineries can try to source certain crudes from certain areas of the world that have lower sulfur. Now, the flip side to this is that it's not always possible because you're depending on market availability, and it may not be feasible from a cost standpoint. So they have to weigh all of these things out. They can also turn to alternative fuels. They can blend. They can do things like they can blend portions of biodiesel, FAME, fatty acid methyl ester. These biodiesel fuels are, they have no sulfur in them, so they can take, a certain percentage of those and mix those into their final blend, and they can, get a little bit of bump or reduction there with the sulfur level. All of these things, but especially the hydro treating of that fuel, the desulfurization processes that these go to, this gives these alter the essential properties of the fuel. And for what we're talking about here, for cold flow, for that, specifically with respect to cold flow, the desulfurization processes alter the paraffin wax content and the paraffin wax distributions in that fuel, and that dramatically changes the cold flow problems that today's ultra-low sulfur diesel fuels have. So paraffin waxes, what are they? What are paraffin waxes in fuel? Well, they are the molecules that contribute most directly to cold flow problems. They're long chain carbon molecules. Some of them can look like this. They may have certain branches coming off of them, but they're long carbon molecules, which means that they're heavy carbon molecules. Because they're long, they contain lots of carbons. Like this one has 24 carbons in it. So they're long, they contain lots of carbon, which means they contribute substantially to the heating value in the fuel. A molecule like this, if you burn it, it's going to create a lot of heat. It's going to create a lot more heat than if you burn methane, which is single carbon. So they're in the fuel, they make up part of the heating and the energy value of the fuel, and when the fuel gets processed and hydrotreated and desulfurized, these fuel paraffins, they get chemically altered, resulting in a phenomenon where they come out of solution. They become insoluble easier in cold weather than the same fuel would have in times past. Now, as diesel fuel cools, as the temperature drops, as the ambient temperature goes down in the winter, these straight chain paraffin waxes that are in the diesel fuel, they become insoluble and they come out of solution. And so you have one of them here, and then suddenly other ones start to appear, and over time, this guy appears, and this guy, and this guy, and this guy, and they might bump into each other, and they might start to stick together. And then these guys will meet other paraffin waxes, and they'll stick together, and you'll start to get this larger and larger and larger agglomeration of crystals and wax molecules. And eventually you end up with a crystal that's large enough that it and its other friends like it can start to cause major problems. This is just a rundown here of what typically happens at certain temperatures as the fuel is exposed to certain temperatures, how these crystals get formation. So we're talking about, as the temperature drops, what's the progression of crystal formation? Well, as you can see, let's say the fuel gets down to 10 degrees Fahrenheit. Well, at 10 degrees and at temperatures around that point, you're going to get the seed crystals that are forming, what they call the nuclei. And we call the seed crystals nuclei because they become the base in which larger crystals are built, essentially. So as the temperature is dropping from 10 degrees Fahrenheit down to, let's say, 0 degrees, well, you're starting to get visible crystals that are forming because of the nucleation of these seed crystals. And then as it's going down, from 0 to -10, the crystals, they're growing and they begin to, find each other and they begin to adhere to each other. And so they're going from small, They're getting a little bit bigger here. Now they're getting bigger here. And as you progress down to what is the cold filter plug point temperature, the inherent CFPP property of that fuel, as the fuel cools down continuously down toward that point, you're going to get formation of large crystals in the fuel, and the large crystals stick together. And when they stick together, they start to form almost like a matrix, a web of crystals. And that web actually traps liquid in it. So you've got a web of wax crystals, and you get fuel that gets trapped inside of the web. And if that happens to a large enough extent, that then changes the physical characteristics of the fuel such that it gels, it becomes thicker, and it may become unable to flow properly and unable to get through the fuel filter because of all the wax that's in there. Now, here you can see some electron micrographs of what these wax crystals may look like. Now, this set of wax crystals here, this is 120 micron distance here. As you can see, these wax crystals are well, they look almost like sheets, first of all, but you can see their size. Their size is larger than 120 microns. Now, keep in mind that most fuel filters in most diesel trucks, whether it's an older one or whether it's one of the newer common rail systems, those filters are running at like 3 to 5 microns. So when you get a bunch of wax crystals like this, trying to get through a fuel filter that has a 3 to 5 micron size, well, now you're going to have major league gelling problems and plugging problems in that fuel filter, and that engine's not going to be able to function the way that it should. It's very likely it's going to shut down in pretty short order. So the wax crystals, they form, they become large enough that they plug the fuel lines during cold temperatures. What you can also get icing if there's water present in that fuel, and there often is. There can be, it may not even have to be free water. It could be emulsified water. It could even be dissolved water, which is water that you can't really even see with the naked eye. Well, that water, when it gets cold enough, that water is going to freeze, and it's going to cause icing problems. So you get icing of the fuel filters. The ice accumulates in the filter. And then it's followed by waxing. Wax builds up in there. If you have a water separator in your system, it's going to experience icing problems as well. And so you get filter plugging, you get plugging of blocking of the pores in that filter by the large paraffin crystals. And in the meantime, in the fuel tank and in the fuel the fuel lines, the large heavy wax crystals, they're going to agglomerate and they're going to drop out and they're going to form sediments in the bottom of the tank. And so all of this is going to cause a pretty major operational problem for that vehicle or for that engine. Now, we've said that sulfur removal has been the primary driver behind the chemical changes in the diesel fuel that give us the problem fuel that we have today. And these changes have significantly impacted the cold weather performance of the ultra-low sulfur diesel. So let's look a little bit more closely at these changes. So, we can acknowledge that they're true, but that doesn't give us the background and the level of knowledge that we might need in order to understand really on a really essential level how and what is happening with respect to this. So let's look at a little bit of these in a little bit more detail. Now, as you can see on the slide, the changes in the processing of middle distillates, i.e. diesel fuel, they've had to change the processing. They've had to make ultra-low sulfur diesel, and it's resulted in changes to the fuel's chemistry. Now, these changes can be divided or classified to 3 main types of changes. First one is that it's increased the total wax content. It's changed the amount of wax that's able to come out of the fuel. It has also changed the ratio of the wax, because we're going to see in a minute, not all waxes are the same in fuel. And then the third thing is that it's changed the solvency characteristics of diesel fuels like kerosene. And that, as we'll see in another minute, impacts one of the ways historically that the industry has used to try and get around cold flow problems. So all these three changes have given us ultra-low sulfur diesel fuels that do not respond as well to the historical treatments that the industry has used to try and get around the problem. So let's examine each of these three things in a little bit more detail. Okay, first one we talked about was the processing has given us a relative increase in the amount of precipitated wax that comes out of solution when the fuel gets cold. Now, what you can see here, you can see data that is illustrated by this graph. It's a comparison of high sulfur diesel fuel here, the orange, and low sulfur diesel. Remember, low sulfur diesel is 500 parts per million. That's the green. And then ultra low sulfur diesel. You can see a comparison of, as you get, as you get colder temperatures, you measure the percentage of wax that has come out. So it's a comparison of the amount of wax that comes out of each of those three kinds of fuels relative to the temperature around it. Now, the results of this depiction here should be pretty clear. What you can see is that there's a significant divergence in the amount of wax that comes out between high sulfur, low sulfur, and ultra low sulfur diesel fuels. The ultra low sulfur diesel fuel has markedly higher percentages of wax that come out of solution as the temperature drops. The gap really starts to widen right around here, right around minus 10 degrees centigrade. Now, just keep in mind, these are centigrade temperatures. These are not Fahrenheit temperatures. So at about minus 10 degrees centigrade, you start to get a divergence. So as you go down to minus 15, historically, when you had high sulfur diesel, and then even when you had low sulfur diesel, you might have gotten, we'll call this a quarter of a percent wax. Well, now you've got twice as much wax coming out with the ultra low. You've got 0.5%, and the gap starts to get larger and larger and larger. You get down to 17%. You'll notice that the percentages are increasing at a greater rate for all of the fuels, because you can see from the slope of the line here. But the rate of increase for ultra low is even larger. So the slope of the ultra low sulfur diesel line is even sharper than the lower sulfur diesels. Down to 20 degrees, minus 20 degrees centigrade, you might have 0.7% or 0.75%. Well, with ultra low, you got more than twice that. Let's say 1.6. And then as you keep going down, you can see it's a larger and larger and larger percentage of precipitation that's coming out of that fuel. Now, so this is a good practical illustration of how desulfurization affects diesel fuel in cold weather. Now, the desulfurization doesn't just affect the total amount of wax coming out, it also affects how that wax is distributed. Now, what do we mean by that? Well, wax distribution. Remember that these waxes, they're different size molecules. We're going to see some distributions here in a minute that will be able to clarify a little better what we're talking about here. But basically, you've got a number of different sizes of these wax molecules. What happens when you desulfurize the fuel is that that distribution of different size molecules changes, and that affects how that wax comes out of solution or becomes insoluble in cold weather. So as you can see on the slide, the ratio of what they call N paraffins, normal paraffins. Just think of paraffin. When you see N paraffin, just think paraffin wax. The ratio, the distributions of paraffin and wax crystals in a particular fuel really impact or influence how wax crystals form in that fuel and how they come out of solution. So when they had to institute hydrotreating and other changes to the fuel to get that sulfur out, that shifted the ratios such that the fuel now performs much more poorly in cold weather than it did before. And if you can get a fuel sample and if you can perform a wax distribution test, you can start to see or predict how that specific fuel sample that you have or that your customer has, how that's going to perform in cold, not only how it's going to perform in cold weather, but also when you try to use cold flow improvers in it, how effective those cold flow improvers are going to be. So you can see 3 wax distributions here. Now, these were each generated by taking a particular fuel sample and running a lab test. And the lab test basically is able to find the number of different size wax molecules in it and then arrange them by weight. So this is the distribution of the different size waxes in these fuel samples. Now, these are all low sulfur diesel fuel samples, so we'll just keep that in mind. Now, down at the bottom, you have the number of the paraffin wax crystals ranged by number of carbons. So these are 10 carbons, 11 carbons, 16, 17, up through 25. And then on the y-axis, they're charting the percentage by weight that each of these sizes are present. So all fuels will tend towards one of these kind of distributions. These two here are this one here is what would be a statistician would look at this and say that looks like what we call a normal distribution. It's like a bell curve. You've got kind of a relatively even rise and fall. I think everyone has seen a bell curve in math class. And this indicates that you got a relatively even, not completely even, but a relatively even distribution of wax crystals. The really small ones, there's approximately equal amounts of really small wax molecules as there are really large. And they tend to peak, have the largest components or the largest amounts, around 16, 17, and 18. Now, why do these distribution matter? You've got a normal, you've got what they would call a narrow one here. And it's narrow because if you look at this one compared to this one, you can see that the middle part here is higher and the ends are smaller. There's this one here, this fuel sample had, 1 point something percent of paraffins that have 25 carbons. This one had none. These ones have probably gone into here. But so this is a narrow distribution. This is a normal distribution, and this is what they call a skew. And you should be able to guess why they call it a skew, because instead of being clumped in the middle, they're really more clumped in this range here. So normal, narrow, skew, 3 different kinds of distributions that you will commonly find in any fuel sample that you have out there in the market today. Now, why does this matter? Why are we talking about this? Well, knowing or being able to see the distribution of a particular fuel sample can help us predict how well that fuel will respond to cold flow treatment. Now, if the distribution of a fuel has a greater number of heavier paraffins out here, then what experience has shown the industry is that particular fuel may be more likely to gel at higher temperatures, because these heavier ones are the ones that are going to come out of distribution or out of solution first. So this particular fuel sample that had the skewed one, and it had a higher amount of larger molecules than, let's say, this one had. You see the difference. This fuel sample is probably going to have a cold filter plug point temperature that's higher. And higher, in this case, is not good. Higher is bad. Practically, it's not that it's harder to treat a cold flow. It's harder to treat for cold flow a fuel that has a narrow distribution like this one, because of another phenomenon that they've noticed, which is that if you have a more narrow distribution of crystals, or of molecules, excuse me, if you have a more narrow distribution, then the waxes will tend to come out at an uneven rate. If you have waxes that they don't come out of solution evenly, what they do is they tend to come out, more of them tend to come out earlier in the process. Now, the key to that is not the earlier, the key is the more. Okay, it would be just as much of a problem if more of them came out late. The key is that you don't get an even dropout, where you get an uneven dropout. And if you have cold flow treatments in the fuel that are waiting for these to come out, then if you suddenly get a large appearance of wax crystals, then the cold flow treatment that you have in there is going to be less effective at keeping all of those apart and keeping all of those treated. So a narrow distribution here, this fuel is going to be more problematic for treating, if you're using a cold flow improver in here, because its wax distribution, its wax molecules are going to come out at uneven rates because of the narrow clustering of the sizes, as opposed to this fuel sample that has a more even normal distribution. Now, that one that we looked at here, this one here, remember, this one's called a skew, and it's called a skew distribution because, well, look at the size. You can see a difference between this and this, right? So fuels that have skew wax distributions, they generally tend to have a higher proportion or higher percentage of their molecules that are lighter. So they usually tend to skew towards the left, not necessarily towards the right. Now, as we were just talking about, that's a problem because this kind of fuel is going to have an uneven precipitation of waxes as it cools down. So more of them are going to come out of solution faster, and the cold flow improver that you have in that fuel, I mean, it's going to do what it can, but it's as effective as a fuel with a different kind of distribution. Sometimes you can also have a what they call a dumbbell configuration. I'm not sure just how common these are, but a dumbbell distribution, I mean, you can see right here, you got up and up like that. So you don't have a nice smooth or relatively smooth curve. You have multiple peaks like this. Well, as you can probably guess, this kind of fuel is also going to have an uneven dropout of wax when it cools down. And so it's also going to have problems as well. So even wax distribution is good. Uneven wax distribution, whether it's a skew or some kind of dumbbell configuration, is bad. Now, one of the takeaways that we should be able to infer from these past few slides is, if you don't know what the wax distribution is for your particular fuel sample that you're trying to work with, if you don't know, then you are really just shooting in the dark when you're trying to predict how best to keep the problems from going away. You can't necessarily take the results from one fuel sample and apply them to another, because there are just so many different kinds of distributions. It really would be just shooting in the dark, and there's no way to get around that. There's no magic bullet that can help you get around it. You just have to, if you want the best answer, to try and come up with the best solution, then you have to find out information like this. Now, that's not saying everybody is going to. That's just relating, one of the facts of life. We don't like it, but that is, basically that's just the way it is, and we have to do our best to work around that. So, cold flow improvers. Well, many times you'll see them abbreviated as CFI. Now, sometimes when we say CFI, we might mean cold flow treatments in general, or at other times we might mean Bell Performance's specific cold flow treatment, which is trade name is cold flow improver, and internally we refer to it many times as CFI. So what you should see here on your screen is that in order to prevent these gelling problems, it's pretty essential to use some kind of cold flow improver chemical or treatment additive in the fuel. The only other alternative to this, which we're going to get to in a minute, is to treat with kerosene. If you're not treating with kerosene, then the only real solution you have is flow improver treatment. And how effective that cold flow improver treatment is going to be is many times going to depend on the wax content of that fuel. Ergo, you have to have enough cold flow treatment in there in order to address the wax content in the particular fuel. Now, the reason why we mention that should seem intuitively obvious, but in the world of fuel additives out there in the marketplace, there are lots and lots of multifunction additives out there that claim to have some kind of positive effect on cold flow. But a lot of these overstate their abilities to solve this problem, because a lot of them only have very marginal amounts of cold flow polymer in their formulations. So they rely somewhat on consumer ignorance in order to get away with overstating the claims that they make. There's really no way around using an adequate minimum volume of cold flow improver if you want to have a meaningful positive effect on the fuel's cold weather performance. Now, cold flow improvers, they can offer significant benefits. They can significantly improve the operability limits of the fuel, and they can be economical to use at the same time, provided you meet these conditions, provided that they are properly formulated for the specific, we call them regional requirements, but the specific chemistry requirements of the kind of fuel that they're going into, and also provided that you can also use them to maximize performance with kerosene blend. So this is when we start transitioning into talking about kerosene blending. Now, kerosene blending is one of the two preferred methods for cold flow protection historically. And kerosene has really been the preferred method of cold flow protection in really, really cold climates, like up in Alaska, up in mid to northern Canada, where it's really not unusual at all for temperatures to drop down to minus 40 degrees centigrade and stay there for long periods of time. When you get temperatures that are that cold, then it is usually more cost effective. It's usually more economically feasible to just mix kerosene into the fuel instead of trying to figure out how much cold flow polymer to use. So kerosene blending has been the traditional solution for getting cold filter plug point temperatures down where they need to be. Unfortunately, all of these changes for getting the sulfur out of diesel fuel has also impacted the kerosene arm of it. You now have ultra-low sulfur kerosene. Now, ultra-low is good in that it enables, somebody who's blending it into ULSD, ultra-low sulfur diesel, somebody who's blending kerosene, and they can use ULSK, ultra low sulfur kerosene, they can use that and still stay within the, that stay below that 15 part per million sulfur content. But the chemical changes of getting the sulfur have impacted ultra low sulfur kerosene such that it is not quite as effective at doing what it's historically been used for. Not only that, but I, and this one I'm not sure. That this one is a market commentary. So depending on when you're watching this, it may or may not be true for your specific time. But there was definitely a time when ultra low sulfur kerosene supplies were not quite high enough to meet the market demand. Now, the market does tend to be smart, and they were able to stabilize those. But that doesn't necessarily mean that at whatever point in the future somebody needs ULSK, there's no guarantee that they're going to be able to find it and to find it at the right price. Now, the downsides, blending of kerosene into diesel fuel does a good job of getting that fuel down where they need to be. But as with many things in life, there is a flip side. There's a downside or a negative. There are certain negatives that blending kerosene, number one diesel, into ultra low sulfur diesel. There's certain negatives that come along with it. Now, in terms of how much somebody needs to use, these, and the reason why I'm bringing this up here is because all of these are related to or magnified by the amount of the kerosene that they're having to blend into the fuel. So the question is, how much kerosene do they typically need to blend in there? Well, it's typically known that the basic ratios are that for every, if you take 10% kerosene, blending it into ultra low sulfur diesel, it will lower the cold filter blend by about 5 degrees C. So let's say that you have a CFPP of minus 20. It isn't too bad, but let's say that you're living in Nome, Alaska, and the temperature is going to be getting down to minus 50. That means you need to drop that by 30. Well, that means you're probably, if the ratio is 10% for every 5 degrees, well, you're probably going to have to blend 60% kerosene. Now, you can do that, but if you do that, then these really become magnified. So let's consider these a little bit. The first one is that kerosene works by diluting the wax content. So there's nothing inherent, chemically inherent about the chemistry of kerosene that changes the wax content. All that the kerosene is really doing is diluting that wax content. So that's the first thing to keep in mind. That it dilutes the wax content. It does not alter the way the wax grows, which means there are still large crystals that are going to be forming at these lower temperatures. We just learned that if you need a particularly large drop, you may have to use a relatively large quantity. You might have to use 40% or 50% or 60%, depending on how low you need to get it down to. Now, from an operational standpoint, you're going to get less horsepower. With the kerosene, you're going to have an increase in fuel consumption. Well, now, why do you have an increase in fuel consumption? Well, you remember earlier we talked about the fact that number 2 diesel has more energy content because it has larger molecules in it than number 1 kerosene does. So if you're replacing larger molecules with smaller molecules, then you're not going to get as much energy out of it, and it's going to make your fuel consumption go up. Lubricity is a big one. Kerosene is a very dry fuel. And when you start turning it into ultra low sulfur kerosene, now it's really dry. So it's really important, if somebody is blending large amounts of kerosene, it's really important that they also look at a lubricity additive. There are a number of effective lubricity additives out there on the marketplace, including Lube Pro from Bell Performance. They can also even try blending in a little bit of biodiesel, although that can cause problems in itself because biodiesel is even less tolerant of cold flow than petrodiesel is. So we'll scratch the biodiesel. They may not want to do that, but they can add a lubricity additive along with it, and that will solve their problem, protect their fuel injectors and their fuel pumps. And then the last one is it's an economical one. Depending on what the market bears, your cost of the fuel is going to go up because ultra low sulfur kerosene is probably going to be more expensive than ultra low sulfur diesel is. All right, so we mentioned on the previous slide that the hydrogen also affected operationally the cold flow properties of the ultra low sulfur kerosene itself. Now, this consideration becomes relevant when we start to consider whether the whole issue of kerosene blending works as well now as it did in the past. Now, when they take sulfur out of ultra low sulfur kerosene, it affected its cold flow properties just as much as taking sulfur out of ULSD affected its. Now here, what you can see is data reflected in a graph that shows how the cloud points of kerosene have changed as it is increasingly processed for sulfur removal. Now, remember, this is CP, cloud point of number one diesels / kerosenes. These are the temperatures here. I believe these are all centigrade. And then you have low sulfur LSD1, which is low sulfur. This is a sample. This is a kerosene, a low sulfur kerosene sample, number one. Low sulfur kerosene sample number two. Then very low sulfur kerosene 1, and 2. Very low and then ultra low. So typically low sulfur kerosene historically gelled at somewhere around -50 or below. But this one, as you can see, it was about -50. That's pretty low. That's gonna cover you in most places around the world. A second sample of it gelled at around -48. Again, pretty low. So we'll say -45 to the low -50s, maybe even a little bit lower than that. Now, when you remove some of the sulfur, you process it, you hydrotreat it, you remove some of the sulfur. Now you've got very low sulfur, which still isn't even ultra low. I don't know exactly how much, but we'll say for the sake of argument, these are 500 parts per million content. Let's say that this is 75. Well, you've got a significant change here. You can see that this one gels at probably about 10 degrees warmer than this one does, and maybe 15 degrees warmer than this one does. Now, if you keep going and you are able to turn that kerosene into ultra low sulfur kerosene, 15 parts per million sulfur content or less, what do you see? You're settling in the low 30s here. So if you're somebody who's trying to blend some of this into your ultra low sulfur diesel to try and get the CFPP point down to, let's say -40, then this isn't really going to solve your problem. So this data here shows that the ultra low sulfur kerosenes of today do not quite do as good of a job of this as they did before. Now, one thing to keep in mind here, these are cloud points, okay? These are not cold filter plug points. Now, remember, we said that cold filter plug point tends to track cloud point, right? So in order to anticipate the cold filter plug point of this fuel, you would go 10 degrees below. So for this sample that's clouding at -32, when's it going to gel? Well, the only way to know for sure is to test it, but if we're trying to extrapolate and be predictive, take 10 degrees, it's going to get down to, the low -40s. Still not anywhere near as good as these, and still, still indicative of the problem that processing of ultra-low sulfur kerosene has reduced its effectiveness in getting, ULSD cloud points and plug points down to the really low temperatures in these frigid climates. Now, another problem, another change is that when they started looking at solvency data, how well these things dissolve the waxes, how well they keep them apart, what they found is another problem. They found that the ultra low sulfur kerosene was not nearly as effective at solvency as its low sulfur cousin or its low sulfur parents were before. And you can see this reflected in the data here, which is you've got temperature in Fahrenheit here, and then you've got a percentage of blend here on the x-axis. And what you can see is that you've got a couple of different samples here. You've got ultra low sulfur represented by the, we'll call it pink, and you've got low sulfur represented by the blue. Now, what you should be able to see here is that as you blend in 10% into ultra low sulfur diesel, what you see is that when it was low sulfur kerosene, it all started at 8. So the base fuel had the base fuel was at 8 degrees Fahrenheit. When you blended 10% into it, if it's 10 ultra low sulfur kerosene, there's no change. Whereas before you could get a 2-degree drop. Now nobody's going to stop at a 2-degree drop, but 2 degrees is 2 degrees. As you increase the percentage down to 30, well, what used to be that you would get a drop from 8 down to -4, or that's about a 12-degree Fahrenheit drop. But with ultra low sulfur kerosene, you're only looking at an 8-degree drop. And then what you can see is that the drop, as you're increasing the ratio here, the drop in temperatures, they're tracking each other, and that's good. It's just that you're still only going to get about let's say a 6-degree difference, 6-degree difference, 6-degree less drop if you're blending ultra low sulfur kerosene versus the old low sulfur. This data here, combined with the data on the previous slide, seems to indicate pretty clearly that the ultra low sulfur kerosene, while it still has some utility, it's not, if they're expecting exactly the same results as they did 10 years ago when they were using low sulfur, that may be a problem for them. All right, so besides kerosene blending, the other main alternative for improving cold flow properties of a diesel fuel is to use a middle distillate flow improver. That's the official industry term for the middle distillate flow improvers, because diesel fuels are considered to be called middle distillate fuels. We call them cold flow improvers. So if you're not blending kerosene, your only other real alternative is to mix in a cold flow improver. And cold flow improvers act by taking the wax crystals that come out of solution, and they basically attach to them and they keep them away from each other. It's basically a dispersant. Kerosene is a dilutant. All it does is it dilutes the fuel so that they're not as able to come in contact with each other. While cold flow improvers go one step further, they actually work by interfering with the individual wax crystals and actually keeping them away from each other. And that proves to be more effective, not necessarily at the really, really frigid temperatures, but at the temperatures that you're more likely to have to deal with when you're in a place like Chicago or Wisconsin, as opposed to Alaska. So cold flow improvers improve the fuel's operability by, as you can see on the screen, doing a number of different things categorically. They They change the way the wax crystals grow. They can modify their shape. They can make them form smaller crystals. They can keep them from sticking together, which is avoiding subsequent agglomerations. And from a practical standpoint, one of the benefits that gives you is that it prevents them from forming that impenetrable film on the filter that shuts off fuel to that engine and ends up shutting down operation of that. Now, from a practical standpoint, this is good because it basically gives the engine more time when it's starting to be able to warm up. Because if you can get the fuel flowing and if you can keep it flowing while the engine operates, starting from a cold start, then eventually what's going to happen is that engine is going to get hot, and that's going to cause the fuel to become hot, because if you remember from anything about how diesel engines work, nowadays they have a certain amount of that fuel that's circulated to cool the injectors, and that warms the fuel up. So use of a cold flow improver allows the engine sufficient time to be able to operate without problems, to warm up, and once that fuel's warmed, you're not going to have waxing problems, because it's going to be the temperature of the fuel is going to be high enough that the wax is going to melt and it's going to go back into solution. Now, we have two fuel filters here, right? One of them was treated with performance, and the other one was treated with a different kind of anti-gel or pour point depressant product. Now, the reason why we're showing you this is because different middle distillate flow improvers, different cold flow treatments can impact the wax crystals in different ways. And if you look at what these wax crystals look like between the two kinds, you can see that there's a difference between the two. This one here, first of all, you can see that this filter here appears to be more clogged with wax, more gelled, so to speak, than this one is. Now, if you look at the crystals, you can see why. Here you have these crystals that kind of look like, I don't know, they kind of look like shards of glass. But these crystals, this compared to this, well, these are obviously smaller. They almost look more like grains of rice. You've got shards of glass here, and you've got grains of rice here. Well, these are small enough that they're going to be able to pass through this fuel filter a lot more easily than these ones pass through here. And so from a practical standpoint, the Bell cold flow improver was more effective at doing what it was supposed to do than this other anti-gel product. And that was because the Bell middle distillate flow improver, the Bell cold flow improver, the formulation of it, it was created in order to contain what is most needed to provide the best benefit. Now, that I know that phrase in and of itself doesn't really mean anything, so we're gonna dig into that a little bit more. If you're trying to create a cold flow treatment that is going to give the best results for the most kinds of fuel, the most most often, you're going to need to have a couple of different kinds of ingredients. A cold flow improver, just like a stability agent, a cold flow improver is not one thing. A package or a combination of two or more different kinds of active ingredients. If you've gone through the stability training that we've done, you know that a good stability treatment is actually a package of different kinds of active ingredients. It's got a metal deactivator, it's got a dispersant, it's got an antioxidant, it's got a couple of other things. But people know the package as a stability treatment. Well, same concept with cold flow improvers. You need to have wax anti-settling agents, or what they'll shorten that, but they'll call them WASAs. So wax anti-settling agents, and then anti-dispersants. And really, this wax anti-dispersant, I'm not sure why they call it an anti-dispersant, because what it actually is a dispersant. So we're just using the what it's called within the industry, but you need something that is a wax dispersant, and you need an anti-settling agent. Now, an anti-settling agent, let's talk about the first one first. It has a certain kind of chemistry that keeps the waxes evenly dispersed through the fuel, and what that does is that it enables them to have essentially the same weight throughout the entire fuel. And practically what that does is they say stay suspended in the fuel longer. I mean, think about it this way, right? You know, if you're trying to keep something floating in fuel, let's say that you have 100 wax crystals that you're trying to keep suspended in the fuel. Okay, now if you keep them all apart, if you put them into the fuel one by one by one by one by one, so that you have 100 individual crystals in the fuel, each of those is size 1 essentially, right? Because you've got 100 of these size 1 crystals, and they're going to probably be light enough that they're going to stay suspended or dispersed. They're going to stay floating in that fuel for probably the longest period of time possible. But what happens if you have, let's say that you have, 10 of them that are size 1, and then you have 16 of them or 18 of them that are size 5. You have 18 bigger ones. Well, the bigger ones, they're large enough that they're got a greater chance of settling out or sinking faster. So ideally, what you want to do is you want to keep them small. You want to keep them of an even size. And if you do that, you have the greatest chance of keeping that wax dispersed and floating in that fuel for the longest period of time. And so that's basically what anti-settling additives do. They try to keep the paraffin waxes at an even weight distribution, which increases the amount of time that you have before they start to settle out of the fuel, because they're evenly dispersed, so they're less likely to plug filters. Now, you can see a simple illustration here of how these anti-settling agents act on the fuel paraffins. Here you have what they call co-crystals. That's a fancy chemistry name for wax crystals. You have wax crystals that were not treated with an anti-settling agent, and what happened is that they stuck together, they formed larger ones, and or they agglomerated, as they say. And so these ones are going to settle out of the fuel at a much faster rate than these ones will. These ones were treated with an anti-settling agent. That's the red here. The anti-settling agent is keeping them apart, which means it's keeping them smaller, which means it's preventing agglomeration, right? And that means these are going to stay dispersed in the fuel and not causing problems for a longer period of time than these ones will. Now, the second one is the wax dispersant. Now, we've been saying dispersant with the on the anti-settling side, so that may be a little bit confusing, because you're like, I thought that the second one was the anti-settling agents being dispersants. And there's a little bit of overlap, but a specialty wax dispersant, well, let's just say that it enhances what the anti-settling agent does. It does a better job. It enhances the formulation's ability to disperse those wax crystals. So you're really going to get your best overall performance if you combine this with an anti-nucleation agent like an anti-settling agent. So a wax dispersant offers further operability gains by keeping those crystals dispersed for the maximum period of time when the fuels are stored below the cloud point. Remember, the cloud point is when you start to see the crystals. So when the fuel is stored and it's cold enough that you should normally be seeing crystals come out of solution, well, having a specialty wax dispersant in that cold flow improver formula gives you the best chance of keeping those wax crystals small and dispersed and not causing problems in that fuel. So we talked about anti-settling. We talked about the two main kinds of things that you need in a good cold flow improver. So let's transition to a practical question. Let's transition to how do different fuel samples out in the marketplace respond to cold flow improvers. I mean, there's been a lot of theoretical talk here, right? But eventually somebody's going to say, well, you know, what benefit is it going to give me? And when they ask that question, what they really mean is how far, you know, what effect is it going to have on the temperature? How far down can it go? So let's talk about that a little bit. If you treat an ultra-low sulfur diesel fuel with a cold flow improver from Bell Performance, what temperature drop should you expect? That is exactly the kind of question you should expect somebody to ask, okay? And the first answer that we typically have to give is, well, it depends on the fuel composition. Now, that phrase, while this is absolutely true, you know, that's not really going to be a satisfying answer for most people. They need to have some kind of numerical idea so that they can take what they know to be true and apply it to their own situation. I mean, they may believe every single thing that we say, and they should, because every single thing we talked about is correct, but it's not going to be meaningful to them until they can take that and they can internalize it and make it frame it in the context of their own experience. So while the first answer is, well, it depends, we need to dig a little bit deeper. And so when we say it depends, we have to say, you know, what are the factors that make it depend? You know, what are the factors that influence things like the wax settling in the diesel fuel? Well, typically the things that influence it are these things you see on the screen. You see, it's first of all the fuel composition, the content of wax, how much wax is in the fuel. If the fuel has a high wax content, then you're going to need more cold flow improver, or you're going to need to add a higher amount of kerosene to dilute it properly to get you where you need to be. And then the second thing, of course, is not just how much wax is in there, but the distribution of it. Is it a skew distribution? Is it more of a narrow distribution, or is it more of a normal? You know, if you can know that answer, which is not to say you always will, but if you can know that answer, you can better predict how that fuel is going to perform. And the main takeaway here is that you need a cold flow improver formulation that can account for the different possibilities in paraffin distribution. Now, when we say it depends, this is when we start to look at data that shows that the answer really is it depends. Now, what you see here is you see a lot of little colored lines here. What we were doing here is we were testing a whole bunch of different kinds of diesel fuels from different places, and they're tested relative to their cold filter plug point temperature in Fahrenheit on the y-axis, and then percentage treatment of cold flow improver in terms of parts per million. Now, if you ever have to convert a part per million to a percentage, all you do is you take the parts per million, you divide it, multiply it by 100, and that would give you a percentage. So if you were to go out to here, let's say you were able to go out to 1,000 parts by volume would be about 1/10 of 1% total by volume. So you see, let's look at the purple. Okay, the purple the purple came from refinery C, and it was supposed to be a winter blend fuel. And you can see that it, you know, with no treatment whatsoever, it's going to plug filters at about 10 degrees Fahrenheit. That's pretty standard. Other ones are, you know, 9 degrees, 5 degrees, and 0 degrees Fahrenheit. Now, as you start to treat these with differing amounts of cold flow improver, what you start to find is pretty interesting. You start to see a very high divergence in the effective drops that you're getting. And what that should tell us is that it's really hard without some kind of prior testing specific to the exact fuel that you're treating, it's really hard to know for sure what drop you're going to get. So let's look at a couple of these. Okay, this purple one from refinery C. Now it started at 10.4. Now when you start treating it with 100, 250, at 250 parts per million volume, you've got less than 2 degrees drop. If you doubled, well, not the, almost double that up to 400, you're still only getting, barely a 4-degree drop. So that particular fuel did not respond very well at all. Now take another fuel. Let's look at the green one. It's from refinery B. Winter blend fuel starts at the same baseline, about right around 10 degrees untreated cold filter plug point temperature. But when you treated it with 150, excuse me, you suddenly you can see that it shoots down to minus 5.8, and then it levels off such that the more you add, if you were to keep going out, you're probably not going to get that much benefit. But that's a pretty big takeaway to go from here to here. And other fuels show exactly the same kind of thing. I mean, this blue one, which is a Harbor fuel batch B, it starts at an untreated cold filter plug point temperature of about 8.6 or 9 degrees. And when you put 150 ppm of Coflow treatment, you got 24 degrees. I think it's 24 if my math, yes, 24 degrees drop. You went from 9 degrees Fahrenheit to minus 13. So the main takeaway here, which should be fairly obvious, is that you can get a very high divergence or very high variance in the effective drop between different kinds of fuel. So given that there could potentially be such a pretty huge difference in how different fuels respond to even the same concentrations of cold flow treatment, then how do you effectively treat this kind of fuel if it's really hard to predict what you're going to get? And that is, that's a fair question, and that's a question that we need to wrestle with if we're going to come away with a good answer. So what are the keys to establishing good cold weather fuel performance? Well, the first key is that you need to use enough cold flow improver. Probably the biggest mistake that people make is that they don't use enough. And as we were saying earlier, some of that is the market's fault, because you have any number of people that have overstated the benefits that you can get. And that, I think, just looking at the state of the industry, I think that has not served the industry well, because it has caused consumers, especially B2B consumers who are always conscious of cost, it's caused them to always expect a cheap solution when, in the reality may be that there is no cheap solution. But when you have 5 different people promising huge results for pennies, and when in fact there's no possible way they can. Well, the fleet manager or the operations guy, he doesn't know any better, and so his expectations get set unrealistically. And then when it doesn't work, unfortunately it sours the entire industry, and that's not a good thing. So the first key is that you need to have the correct concentration of cold flow improver in the fuel. Now, how do you know what the correct amount is? That's the question. Well, let's look at some more data here. Looking for here, you can see this is a graph of volume of cold filter plug point relative to performance. Performance being drop in cold filter plug point, and this is in degrees centigrade. So you've got 1, 2, 3, 4, 5, 6, 7 different fuels, and these 7 fuels are treated with differing percentages of cold flow. Now, these fuels are these percentages here, I believe, are paraffin content percentages. Now, without digging too far into the minutia of this. What you should be able to see is that, first of all of these graphs look kind of sort of similar. I mean, take the green guy here. You go up, 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 up as you're, and then right around 100 ppm, the benefit starts to level off. And so when you're up here, if the operations guy is saying, oh well, we got 19-degree drop at 250, well let's double it, let's get 38 by going to 5. Well, he doubles the amount of cold flow improver, but he doesn't get any benefit. That's because there was a point with that kind of fuel that they stopped getting a meaningful drop no matter how much polymer he added. And that phenomenon is consistent among all fuels. Now, that's not to say that the point at which that happens is the same, but it's what we call the cliff effect. There comes a point where for each individual fuel where your point of your I guess law of diminishing returns is what I'm trying to get at. You can keep adding and keep adding and keep adding, and you don't get any more meaningful benefit. So the original question was, how do you know what the correct amount is? Well, you can make an educated guess based on how the fuel has performed in the past and practically the results that you've gotten. But unfortunately, when it comes down to it, you cannot know specifically the answer for your specific fuel unless you take a fuel sample and you have it tested. Now, that's very important. When the big boys are doing this, they are not relying on guesswork. They're taking fuel samples and they're sending them away to the lab, and they're having cloud points, pour points, and cold filter plug points run on those fuel samples. And what they're aiming to find out is if we know that the plugging point of this fuel sample is X, and we know that it's going to get down to 20 degrees below X this winter, how much added do I need to add? And by testing the fuel sample, basically by running cold filter plug points at varying concentrations, they can know the answer to this. Now, they do this because they are the big boys and they have millions of dollars riding on this kind of stuff. The typical fleet probably does not have millions of dollars running on it, but they certainly have enough riding on it that they would want to have an answer to this. But that's basically how you get the answer, is you run cold filter plug point tests relative to Coflow treatment, and you get a more specific answer. Now, I referenced the cliff effect, and the cliff effect is also illustrated in this graph here. This is a particular fuel sample, and we have its cold filter plug point temperature, which was probably in degrees Fahrenheit was around, we'll call it 12. Now, it was treated with cold flow treatment at increasing concentrations here. And what you can see is, this is illustrative of what we're trying to see here. Right between 50 and 75 ppm is where you start to get a drop. So you're starting to get a benefit around in here. And as you increase it to 100 to 125, you're starting to see substantial drops. When you went from 75 to 125, you basically dropped by 10, 15, 17 degrees. And that's reasonable. That's a good drop. Now that fuel is protected down to about minus 6 degrees Fahrenheit, which is probably good for a lot of areas. But as you start to, as you keep increasing it, you can see something happening here. You can see that the slope of the line is evening out, which means that as you keep increasing by 20 increments of 25 ppm, the benefit's getting smaller. And once you get up to around 200, you're not really getting any benefit increase at all. That's the cliff effect. What that illustrates to us is that it's incrementally more difficult to make to get a fuel's plug point temperature uh, lower and lower and lower as you go lower and lower and lower. So it's much more difficult to make a fuel go from, to go from, let's say, 13 to 14 degrees, excuse me, minus 13 to minus 14 degrees. It's a lot more difficult to do that with this fuel than it was to get it to go from 10 to 9. And that's true for all fuels. Now, the numbers may change, but the principle is the same. All fuels have a point at which they stop responding in a meaningful way to Coflow treatment. So our job and the job of the operations person who's trying to prevent problems on the ground level is to know what that point is so that they don't throw good money after bad with this kind of thing. So first key was have the correct amount in there. Second one is have the correct base of constituents in the formulations. Now, Coflow improvers use certain kinds of base within the industries. They use what's called vinyl acetate copolymers. Now, this kind of thing, this is the base kind of molecule that is the most commonly used Coflow improver. It's a vinyl acetate. Now, there are different kinds of vinyl acetates, and they can be varied by how much of certain kinds of groups they have. I mean, this right here is known as a vinyl acetate group from a molecular standpoint. So they can vary the content, they can vary its molecular weight, they can vary the kind of solvent that it is dispersed in. They can do a number of different things. Chemists can modify these parameters in order to create these copolymer combinations that achieve the best kind of performance. Now, you need the correct synergists in the fuel blend in order to achieve the best results. And what the correct synergist is depends on the fuel's composition. Now, you are not going to have to know any of this in in-depth detail. So the reason why we're talking about this is just so that if you hear about any of this kind of stuff in the future, then it will not be the first time that you've ever heard of it. So, 15, 20 minutes ago, however long it was, earlier in the training presentation, you saw that different wax distributions would influence how different CFI polymers worked. Well, it turns out that there are certain kinds of Coflow resins and Coflow polymers that actually help blunt these effects. For example, you remember one of the distributions, that particular fuel had more of the heavy end waxes, more of the paraffin wax molecules that were the higher carbon numbers, 23, 24, 25. And we said that that could be a problem because those waxes would drop out at higher temperatures. Well, there are certain kinds of cold flow resins like polymethacrylates and alkyl phenols that actually are able to target and treat these heavy end waxes better than other ones will. There's also things called comb polymers. Now, comb polymers tend to functionally work best when you have those narrow range ones. You remember the narrow distributions. You remember the curve where it had less of the waxes on the end, less of the smaller ones on the end, but it had more clustered in the middle. Well, a chemist, a formulator, can take comb polymers and mix them into the package, and you'll get a cold flow improver that works better at targeting that kind of fuel. So a good formulator will, what they'll seek to do is they will seek to come up with a formulation blend that attacks as many of these kind of phenomenon to the best extent possible. Now, the one disadvantage that we have as formulators is that we don't know exactly what we're going to be dealing with. So Bell's cold flow improver treatment is formulated to try and predictively have the best result possible kinds of fuel characteristics. And that, in the end, um, is really the best thing that you can do. But that puts Bell at an advantage over a lot of other places because there are a lot of other formulators who don't really take this kind of thing into account. Now, as we said, having the right or the wrong kinds of components can make a big difference to how that blend, that cold flow improver blend, how that works and how well it protects the fuel. And you can see this illustrated here. This is data, 3 different kinds of fuel, fuel D, fuel E, and fuel F, so 3 fuel samples. And each one of them was treated with 3 different combination blends of synergists, 3 combinations of different cold flow polymer constituents. And what you can see that there are, some cases, substantial differences in how these polymers work with that fuel. Now you can see this is change in cold flow. This says delta CFPP. Delta basically means change. So this is the drop in degrees Fahrenheit of cold filter plug point. Now for fuel D, these two, that's copolymer 750 and then copolymer 750 with another, mysterious ingredient A. Mysterious ingredient A did not really do anything additional in fuel D. In fuel E, mysterious ingredient A actually made it less effective, by 6 degrees. But in fuel F, mysterious ingredient A, made it more benefit by a couple of degrees. The green, I mean, you can see differences here. If you were to look at this long enough, you should be able to see a number of substantial differences. And so without getting too granular, what this should be able to show you is that there are different combinations of synergists really can make a substantial difference in how well that particular package works in a particular kind of fuel. So combining synergists sometimes will give you a more effective cold filter plug point drop than just using individual synergists alone. It really just depends on the kind of what the fuel characteristics are that you're treating. Now, this right here, this is an illustration of different fuels, different diesel fuels from different regions of the United States. And what we're aiming to show you here is how the properties of fuels that come from these different geographic areas can produce markedly different results when you're talking about cold flow performance and winter temperature performance. You can see fuels from out west, in the central part of the U.S., fuels from the northwest, and then fuels from the northeast. Now, what you can see here is each of these fuels were first of all, their cold filter plug point was tested in an untreated manner to establish the base. These are not cold filter plug point, I'm sorry, these are cloud points. So you have the base, which is here. So the base cloud points for each of these was, let's see, 9, 6, 7, and 10. So you're in the 7 to 10 degree Fahrenheit range, which is that's reasonable. But when you start treating them with different combinations of different packages of cold flow, synergists and active ingredients, you start to find markedly different results depending on where in the country that fuel came from. Out west, this CFI comp one, dropped it by, see if we said 9, so that's a 14 degree drop. But then when you use these, you got a huge drop. You got drops down to, minus 17, minus 20 degrees. The same concentrations of the same active ingredients actually produce even greater benefits in fuel from the central part. But when you go to northwest and northeast, you can see the results are much different, and they're not standardized across all of these. I mean, 8500 HE in the central part of the U.S. took a fuel that had 6 degree Fahrenheit and dropped it by we'll say almost 30 degree drop. Well, In the Northwest, it dropped it by, what's this, 7 minus, you dropped it by 5. 30-degree drop, 5-degree drop. And, maybe this is a 7 or 8, but you can see that regional composition of fuels really can make a significant difference to how well a certain kind of cold flow improver package works. So the bottom line here is cold flow improvers do not have exactly the same level of benefit in all kinds of fuel. But proper chemistry can give you a blend, as we were saying earlier. Proper chemistry can give you a blend that has the greatest chance of working the best in the most different kinds of fuel. And because you can't test every single kind of fuel, then really the best thing that you can do is to try and make a formulation that gives you the best chance of result in the most different kinds of situations. And that is what Bell Performance aims to do. The third one, as we start to wrap this up, the third one is you have to be able to prevent fuel icing problems. Now, icing means water. All diesel fuel has a certain amount of water in it. Now, it can be free water, which is, the water phase at the bottom of a storage tank through something like condensation. You can also have an emulsified water, but you can also have dissolved water that's dissolved in the fuel, but you can't really, you can't really even see it. So it's hard to know that it's even there. Yet, when that fuel drops cold enough, then even if it's dissolved water, that water is going to freeze. When it freezes, it's of course going to form ice crystals that are going to get trapped in the fuel filter and cause the same kind of problems that the wax crystals form. So you do have to account for icing, and you want to aim to do something to prevent that. So what what the recommendations are is that a cold flow improver package should have some kind of demulsifier or dehazing component in it. A demulsifier, what that does is it takes dissolved and emulsified water that is normally it's in the fuel and it's suspended in such a way that it's not dropping out on its own, at least not without a very long period of time. It's essentially suspended in the water, or it's dissolved in the water, and it's staying there. If it stays there as the fuel gets too cold, it's going to freeze. It's going to cause problems. So you add a demulsifier, and that actually breaks the bonds that those really micro-sized bubbles of water. It breaks those bonds and it causes them or encourages them to be able to drop out. And that really gives you your best chance of preventing a water fuel icing problem, so to speak. So how do you control water? The recommendations that we typically give, you need to establish good housekeeping practices. That means you definitely want to get rid of free water in your storage tank. If you have free water going into the winter, that's bad news. So we always recommend for our customers that are in outside of the state of Florida. Florida doesn't have these problems all that much, but Florida is only one state in the union. Bell's been doing business in all states for decades. So for our customers that are faced with colder climates in the winter, well, we recommend that they control water. They do good housekeeping practices. They drain tanks. They have the water pumped out on a regular basis. If they have entrained water, then we recommend that they use some kind of demulsifier or de-icer. Now, as we said, Cold Flow Improver has a de-icer in it. And in the other areas of Bell Performance's product line, we do not currently have a specialty demulsifier, but we anticipate that I'll say within the near future, Bell Performance is going to be able to introduce a demulsifying fuel treatment, and that will give our customers and our contacts even more options in being able to adhere to these best practices. So you want good housekeeping practices. You want to be able to drop out excess entrained water if at all possible, and then you want to use these de-icers. De-icers typically, when you're talking about what kind of molecules act as de-icers, well, there's high molecular weight or heavy glycol ethers will do it. If you use them in sufficient enough quantity, then they will get the job done. They work because they have pretty low freeze points, and so they're able to essentially, freeze points below the typical cold filter plug points for most fuels. So if they are part of a fuel treatment package, then they're able to attack the water crystal, the ice crystals, essentially melt them and dissolve them at temperatures before the fuel reaches that cold filter plug point, and the water freezes and the wax gels and all that gets stuck in the fuel filters. So de-icers, especially as part of the cold flow improver formulation from Bell Performance, are pretty essential winter treatment things to use for most places that store fuel and have to use fuel in the winter. Last thing that we want to talk about, we've gone into a little more detail than we have with other training, and that's good because there's a lot of detail that we could touch on even more than what we've been doing. But the last thing that we want to talk about here, we had mentioned common rail diesel engine systems. Now, common rail engine systems, those are, as of 2016, those are pretty much the law of the land, and not the law of the land as in you have to use one, but it's what have become the standard within the industry. Virtually all diesel engines of any substantial size have these common rail injection systems. Now, on the one hand, they're good. They enable diesel engine manufacturers to make diesels that have more power, better performance, better fuel economy, and a lot fewer emissions, so they're better for the environment. These particular, the way that these are engineered and the way that the common rail systems are set up, they're able to do things that conventional engines just historically could not do. And so they are just a better and more advanced diesel engine design. Now, on the flip side, because they are better, because they are more complicated, they're more expensive, and so they have to be protected. And so the engine manufacturers are speccing smaller diesel fuel filter sizes than in previous years. And by sizes, what we mean is they filter out things, particles of smaller size, because they do not want anything like water. They do not want any kind of particulates getting into the injectors and fouling those up, because the injectors are working even harder than they ever have before. Now, when you're flow, well, that has changed the game with respect to the expectations of what you should be able to do in running diesel engines out in the cold. Now, the bottom line here is that if you're going from a 20 micron fuel filter to a 5 micron fuel filter, that means that 5 micron is going to catch a lot more of the wax crystals that previously would have just passed on through. So that means the smaller fuel filter is going to gel faster, means it gels at a higher temperature, which means effectively your gelling temperature is now higher than it was before, even though it has nothing to do with the fuel itself. It has everything to do with the filter that wax is being caught in. And now you may say, a 20 micron to a 5, that's 75% smaller. Okay, that's significant. We use this kind of graphic to show you that using simple geometry, the differences are actually even a lot more magnified than you would think. What this is this is an illustration of the different pore sizes, and then how mathematically those pore sizes actually have a much bigger difference between them than you might think. So this one here, this is the blue one. This is the old 25 micron sized pore. And we could calculate that it has a total area here of 491 square microns. And that's 491 square microns for some kind of particle to pass through, right? Or some kind of wax crystal to pass through. All right. So they say, okay, let's cut it down from 25 microns to 10 microns. Well, you're going from this size here to this size. This is a 10 micron. Now, normally you'd say, what's the proportion drop? 25 to 10? Well, 10 is, let's see, to multiply by 4, carry the 1, 40%. Okay, 40% of 25 is 10, which means it's essentially a 60% drop. So you've got a pore size that's now only 40% as big as it was before. Okay, well, you know, that's a lot smaller, but it's actually a even greater difference than you might think, because when you look at the difference in size, you're going from 491 square microns to just 78.5, 16%. In other words, it's not a 60% drop, it's an 84% drop. And that difference gets magnified the further down you go. If you go from 25 to 5, which this is more likely to be what a common rail fuel filter pore is going to be sized at, 5 microns. Well, 5 microns is 80% smaller than the old 25, but it only has a 19.6 square microns area, which is 96% smaller. And if you get down even smaller, you can see, you know, a 2 micron is 99.36% smaller. So from a geometric standpoint, it's even more, the drop in filter size is even more significant than it would first appear. And so, of course, what does this mean in practice? Well, when we're communicating the implications of this, smaller filters for common rail engines mean higher effective gelling temperatures. And what they're telling us in the industry, they say that normally you would expect cold filter plug point temperatures to be historically 8 to 10 degrees below the fuel's cloud point. But if you're going with a smaller fuel filter, then that means that the effective plugging temperatures are actually 5 to 8 degrees higher than they were before. So, you know, when we're streamlining this and we're not throwing figures out at people, what we basically, and what you basically should be telling the people that you're talking this before is, you're telling them that you know, the cloud point that you used to keep track of, well, your old cloud point is now your new cold filter plug point. That's what you should plan for. That gives them a few degrees margin. So if a fuel used to have a cloud point of 5 degrees Fahrenheit and then -5 or -10 degrees gelling temperature, well, now you're telling them, hey, don't plan on the fuel gelling at -5 degrees Fahrenheit. Plan on it at gelling at 5. Plan on it gelling at what used to be your cloud point. And if you do that, and if you account for that, then you have a much greater chance of not being bitten by this big change. Now, for us, what that means from our standpoint is that it is even more important now to treat diesel fuel with Coflow improver earlier. You do not want to wait until the temperature is below the fuel's cloud point in order to start treating it. You need to have the Coflow treatment in there, present in the fuel, before the cloud point, before those crystals come out of solution. And so with all of these filter changes, it should be pretty evident to all of these people inside the industry that they need to take Coflow treatment of fuel a little more seriously. All right. That brings us to our final notes and reviews. We've spent a lot of time talking here, so appreciate you sticking with me here. Let's just do very brief summary. We're not going to summarize all of this. Main takeaways, what we want to do. Always, as I was just saying, from a best practice standpoint, always remember to add the cold flow treatments at ambient temperatures above the cloud point. Don't wait till it gets cold enough that the crystals start appearing. Add it before the cloud point, above the cloud point. Cold flow improver treatments do not protect against wax that's already precipitated. That's why you need to add it at temperatures above the cloud point. And then how much protection? Well, again, we spent a lot of time talking about that the amount of protection depends on where the fuel comes from. It depends on the wax distribution and all that stuff. But most people are not going to know or have a meaningful knowledge about those factors. So we tell them that if they add enough, they can expect about a 20-degree drop Fahrenheit. That's your baseline expectation. Results may vary, of course, but if you're trying to pick one thing, well, then, that's what we would pick. Last thing, what are the market opportunities from a sales standpoint? And this is where, we would talk to, this would be an internal discussion with Bell Performance. You may not, you may be viewing this as an outside person, and that's fine. With this, though, market opportunities, who are the kinds of people that would be needing to consider cold flow improver and cold flow treatment for a diesel fuel? Well, the first one is not people in Florida. I mean, something like this, all good humor has, it's funny because it has an element of truth in it. And, I haven't seen anybody in Florida at the beach doing this, but, somebody always has a story like that. So not so much in Florida, but places where the ambient temperatures can expect it in any given winter to drop below the cloud point of the fuel. Those people always have to be have cold flow treatment of fuel in their back pocket as a possibility, because that one time that you don't treat the fuel is going to be the time that it gels up and causes you big league headaches. Fleets and businesses in these cold weather climates, especially those that they rely on engines to get the job done, which means all of them, because they all rely on diesel engines to get the job done, or else they wouldn't have them. Long-haul truckers, definitely people with emergency generators. You do not want a winter emergency to happen and not be able to keep your generator running. So emergency generators and emergency backup systems absolutely need to consider cold flow improver treatment of their fuel. And then lastly, anyone who has a strong financial stake in avoiding fuel gelling problems. Anyone who has a kind of business or a kind of enterprise where if their engines can't run because they're going to lose big money, they are going to have big problems. Anybody like that. And that's where you have to assess your own business if you're out there in the marketplace. That's where you have to assess your business. And you have to ask yourself, you have to analyze, how much would it cost me if I could not get the job done at any particular time because my fuel was gelled? And you will probably, very likely find that the cost, if you analyze all of the costs associated with it, you're very likely to find that it's going to be in your financial best interest strongly to spend a little bit on some preventive maintenance, like making sure that your fuel is treated to prevent cold flow problems. And that, my friends, brings us to the conclusion of our training on cold flow issues with diesel fuel. Now, we have gone through a lot here. You may have some questions. So my email's up on the screen, ebjornstad@bellperformance.net. If you have any questions, then feel free to email me. Just mention that you were watching the diesel cold flow training, diesel cold flow presentation. Let me know what you need. I will be glad to try and help you in any way I can. So that concludes our training for today. I am Eric Bjornstad with Bell Performance. And thanks very much for joining me. We'll see you next time.